Hello. Okay, I want to go over question 3 from this week's recitation because I just think I believe not many recitations were able to go over it, and it's a little bit, can be a little bit confusing. So, what's the question? We start with two lists. We start with an orders list of order A, order B, order C, order D, order E, and a painting list of PA, PB, PC, PD, BE, PE. And what you can think about is that these are each in order for something. So maybe we have like an A, a B, a C, a D, a E order. And what we want to do is process these orders with a couple of restrictions. The first one is that you can only process an order after its order time. After order time. So if we look at the B order, we can only start processing it after the order B time. The second is that once you start an order, you can't stop. So you're going to start order B, you start it and it's going to take that painting time of B, and you have to spend that amount of time before you can do anything else. And that's the goal. And at the end of this, we're going to get a lot of finish times. We're going to finish order A at some point, we're going to finish order B at some point, and we're going to call each of these TA, TB, TC, TD, and TE. And what our goal is to minimize the sum of these TI values, the sum of these finish times, which would make sense. In the real world, you're going to want to finish these orders as quickly as possible. And so our goal is to finish the sum of these. The issue is that this is an NP hard problem. So this is the restricted version, and it's NP hard. So we can't do it. So what we're going to do instead is look at an easier version of this problem and try to use it to help us. And so what you might be thinking is that I keep using the word restricted, and that's because we're going to have an unrestricted version. And here's how the unrestricted version works. We have the same condition that we can only start a process after the order time. So, okay, we can only process an order after the order time. Now here's where it's different. Because in the restricted one, we said that that the moment you started one, you had to finish it. You had to go until the end and finish it. In this one, we have a pause function. So in this one, it's that you can pause an order and then move on to something else. So we're going to pause it, and this is what we're going to call the unrestricted version. Unrestricted. And this we can actually do in polytime. There's a way to solve this. Okay. So that's the set. We have a restricted version we want to solve. We can't do it. We have an unrestricted version we can solve, and we're going to try to see if that can help us figure out what this minimum sum is. So I'm going to erase. Okay. So now let's take a step back. We have our inputs, we have our order list and our painting time list, and ideally we want to get this restricted finish time list. We don't really know. Oh, shit. Oh, no, we're fine. So the idea is that we have this unrestricted black box. That we're going to chug these things in, and it's going to get us a different finish time, a different finish list. And we're going to have something similar. We're going to have a TA, but we're going to have a TA prime. So TA prime, TB prime, TC prime, TD prime, TE prime. So this is the idea. So we're going to chug this into our black box. We're going to get a finish list. And it's probably going to be completely different than what the finish list would have been with the restricted version. Who knows what differences are? Maybe one of the, so much is in the air. The other thing we're going to do is I'm going to sort this. So I'm going to want to know, okay, I have my finish time list. What was the order in which I finished these paintings? So this is going to be something different. So maybe the sorted version looks like TD prime finished first, then TB prime, then TC prime, then TE prime, TA prime. Who knows? But we're going to sort this and look at specifically the sorted order of how we finish these projects. Now, a note on indexing for the problems, because there's going to be a lot of indexing here. In this one, when we index into the restricted array, or in the finish time of the restricted problem, we're going to call this TI. TI. When we index into the unrestricted version, in the order that we were given, it's going to be similar. We're going to index into this with TI prime. Now, when we index into the sorted array of the unrestricted one, we're going to call this TJ prime. And then if you wanted to, you could also say, well, let's say that we had a TJ, if we sorted this, if we had sorted the restricted list. So this is our indexing scheme. We have two different indexing schemes, and it's important to know which one's which. So that's where we're at. Now let's do some inequalities with this. The first one, let's look at TC prime in here. We finished at third of these. We finished project D and project B before finishing project C. What does this mean? Well, here's our first inequality. TJ prime has to be greater than or equal to the max from k equals 0 to j of the order times of k. What does this mean? TC prime, or the C project. We know we finished D before it. We know we finished B before it. Which means, or let me take a step back. TC prime has to be greater than or equal to order C, the order time of C. You can't finish a project before the project is ordered. So TC prime has to be greater than or equal to order C. But we also know that TC prime had to be greater than order B, and TC prime had to be greater than order D, because we finished those two projects first. You can't finish order B and then finish order C, but somehow finish C before you had ordered B. It wouldn't. It doesn't work. So we know that our finish times has to be greater. And you could use that logic for any one for any index in this sorted array. So that's the first inequality. Here's the second one. Tj prime is greater than or equal to the sum from k equals 0 to j of p of k. What does this mean? Well, actually has a very similar reasoning, which is that we know we spent at least the painting time of D plus the painting time of B plus the painting time of C before we were able to finish project C. So we know TC prime has to be greater than or equal to PD plus PB plus PC, because this is the time that we had to spend before finishing C. And so those are the two inequalities we get, both of them coming from the fact that, like, well, you had to do some, by looking at, like, the work that you had to do before finishing at, like, this index, or the project at this index. Okay, so that's this. Now, here's what we're going to do. How do we use this, so we got this from, we plugged our inputs through the unrestricted black box and got these two arrays. What we're going to do is we're going to use the sorted array as a blueprint to find an answer to the restricted problem. So we're going to use, the sorted unrestricted solution as a blueprint. As a blueprint for the restricted solution. So here's how we do that. We're going to assume that the restricted problem finished painting in the same order that the unrestricted one did. So we're going to assume the restricted solution finished in the same order. Why do we do this? Well, this is going to get us a solution to the restricted problem. It might not be the best solution, but the reason we can do that is we know that the optimal solution to the restricted problem has to be less than whatever we get out of this. We're limiting ourselves to only situations in which we finished in the same order, D, B, C, E, A. So what can we do in this situation? Here's what we know. TJ. So we're going to look at the jth thing we finished in the sorted list, in the restricted problem. We can conclude that this has to be less than or equal to the max of k equals 0 to j of OK plus the sum from k equals 0 to j of pk. What does this say? Well, so let's look at C again. In our restricted list, in our sorted list, the third one is TC in the sorted list. Which means, at the worst case, what you could do is wait until the max, you could look at like these first three guys. Wait until the maximum, until like the last order comes in. And then paint everything in this order. And you just wait till it comes in, paint everything, and bam, you're done. And that would be a valid solution to the restricted problem. If you once you in the situation in which you know you finish in D, B, C, E, A order. And so this is a valid solution, which means in any situation in which we finish in this order, the finish time of TJ in this sorted list has to be less than or equal to this. Okay. But now we also know, we also have these two inequalities, which means that this is less than or equal to 2 times tj prime. So we know that like the finish time of C in the restricted list has to be less than or equal to 2 times the finish time of tc prime in the sorted list. And that's what we get. And using this inequality and finishing it all off, we get that the sum, of tj's is less than or equal to 2 times the optimal solution. No, let me do this. 2 times the sum of tj is less than or equal to 2 times the sum of tj prime. Hold on. J prime, which is less than or equal to 2 times the optimal solution. Because this was something that we had proved, this was something we had mentioned kind of at the start, which is that the sum of these guys has to be less than or equal to 2 times opt. And now you're done. Which means, to summarize, we started with our inputs. We use them to get just a plain finish time and a sorted finish time. We then used the finish time order to analyze what we could do in the restricted version and bounded those finish times. Alrighty.